Okay guys, so when I was going back through my lectures, I remembered that we had forgotten, or we hadn't had time to go over this video. So, once you begin with this video, I'm going to be stopping and giving you some vocab terms throughout this video. It's a 43-minute video, but we're only watching the first 11 minutes of it. You can go ahead and watch the rest if you feel like you want to learn more. And then you switch over to the next lecture, Solar System Lecture Part 2, and that will give you the rest of the lecture for this series and for the quiz on Thursday. So, planet building. Okay, so this is a video how the Earth was formed, and when we like I said, we're going to be stopping through and flashing back to the PowerPoint in order to give you some vocab terms.
This episode travels back in time to investigate the greatest geological mystery of all, the birth of the Earth. Scientists explore how our planet first formed from the dust of the solar system, how molten rock solidified to land, how our oceans filled with water, and how life arrived on Earth. These are the earliest chapters in the incredible story of how the Earth was made. When it comes to finding clues to the birth of the Earth, our planet has been good at covering its tracks. Billions of years of erosion, volcanic activity, and the shifting of continents and oceans have destroyed almost all the evidence of the earliest stages in Earth's formation. For geologists trying to discover how and when the Earth first formed, this is a major challenge.
As geologists began to question the age of the Earth, and of course they looked for older and older rocks, what we began to find was that the further back you go in Earth history, the harder it is to find any of those rocks.
The search for the oldest rocks on Earth brings investigators to the harsh desert landscape of northern Arizona. This giant hole in the ground is Meteor Crater, formed when a massive meteorite slammed into the Earth.
We didn't really have rocks from the very beginning. Well, where could we find something? What about the meteorites that have been out in space and fall on the Earth?
It was here that geologists made a vital discovery. Meteorites are older than any rocks on Earth. They had found the key that would unlock the secret of Earth's formation. If the oldest rocks came from space, that is where the investigation must begin, in space. Our solar system, 4.5 billion years ago. At its center, the young sun.
The theory that emerged was that the sun was surrounded by a cloud of dust and gas, and as that cloud cooled, little grains of minerals formed. So all these little grains of minerals floating in this gaseous cloud are moving around the sun, and they start to bump into each other.
But there was a problem with this theory. Nobody could explain how colliding microscopic mineral grains could ever create an object the size of a planet. Then, in 2003, an experiment on board the International Space Station accidentally provided extraordinary new evidence. Astronaut Don Pettit wanted to see what happened to different substances in the zero-gravity conditions of space. He did a simple experiment by pouring some salt into a plastic bag and shaking it. The results were astounding. The particles immediately began to stick to each other, forming little clumps, all held together by tiny static electric charges. Scientists realized that if grains of salt stuck together in space, then so could the mineral grains in the solar dust cloud. Here was real evidence for the fundamental mechanism that kick-started the formation of the Earth. As mineral grains...
Okay, so as these mineral grains are forming, we get what's called, these are all your vocab terms, planetesimals. So planetesimals are one of the small bodies that formed from the solar nebula and eventually formed a planet. These specks of matter, whatever the composition, so if they're hydrogen or oxygen or iron, they grew from microscopic by two processes. So, okay, so atoms built together became compounds and so forth by the two processes of condensation. Okay, so the first process that formed these planetesimals was condensation, which is the growth of a particle by addition of material from surrounding gas atom by atom. Okay, so building these atoms, hydrogen to hydrogen, hydrogen to helium, and so forth. As the grain grows larger, the method of condensation becomes less and less effective. Okay, so condensation becomes less important as these particles or these small planetesimals get larger and larger. And that's when the accretion process becomes important. So accretion is the sticking together of solid particles to produce a larger particle. Okay, so we get condensation from this protoplanetary disk around the sun that's initially forming these small, or bringing these atoms together to form small planetesimals. And then once condensation is no longer effective, we get accretion. So larger particles are allowed to come together and become even larger. And that's when we eventually get to our planetesimal size. Let's go back to our video.
In the solar dust cloud bumped into each other and stuck together. They grew into small pieces of rock orbiting the sun. Over the next few million years, some of them collided and grew bigger. Many of these rocks are still orbiting the sun today. They have drifted for the past 4.5 billion years, unchanged from when they first formed. Occasionally they fall to Earth, and we call them meteorites. They provide scientists with an incredible window onto the past.
We brought what's called a stony type of meteorite. What the scientists do then is slice across it and look on the inside. And to a planetary mineralogist, you start seeing all kinds of wonderful things.
This meteorite contains minerals and metals from every part of the solar dust cloud.
So what we're looking at is the assemblage of all these little ancient materials that were floating around the sun in the nebula of dust and gas. And when they hit each other, they gradually aggregated into solid bodies, which got bigger and bigger.
Gradually, billions of these rocks grew as they orbited the sun. First to the size of boulders, then as big as houses. And they kept on growing. When an object reached about half a mile across, its own gravitational pull became strong enough to draw other objects towards it.
Some object in this huge number of objects going around the sun, one of them had to be the biggest. And as soon as it gets bigger than the others, it's sweeping up more objects, just like you're driving through a cloud of mosquitoes at night in your car and the front windshield's getting hit more often. So the bigger it is, the faster it grows, and the faster it grows, the more gravity it gets, and that pulls in more objects. So the biggest object starts to run away from the crowd. It starts to grow fastest.
And that biggest object was the fledgling Earth.
Okay, so pause there. This fledgling Earth that they're talking about is what we consider a protoplanet. So going back here, we have the accretion process. That's what they were talking about with them getting bigger and bigger. And then we get these protoplanets. So protoplanets are massive objects that are destined to become planets. So in that where we're at in the video, where we have Earth just becoming Earth, this is what we call a protoplanet. As protoplanets grow, new processes begin making them grow faster, and this is something that you've heard on the video as well. And they alter the physical appearance as a result. So like we're seeing with Earth at this stage in the movie, you know, we're seeing a more molten object and so forth. And that all has to do with this process of these particles coming together at faster and faster rates, and producing this, producing these protoplanets. Not that one. Here we go. So many windows to open.
Soon, the young planet had so much gravitational pull that it began to attract bigger and bigger objects. As they crashed onto its surface, Earth's size increased with every impact. The bombardment was so intense that it only took about 30 million years for the planet to grow to almost its present size. The young Earth was made of billions of pieces of rock randomly stuck together. But geologists know that the modern Earth is not like that. Below the surface, Earth is separated into distinct layers. A thin crust, then a massive dense layer of rock called the mantle, and at the center, an iron and nickel core. Some extraordinary event must have occurred to transform the interior of the young planet. Geologists now believe that soon after it formed, the Earth completely melted.
Originally, the Earth was probably just a big collection of rocks like this, but it heated up to the point where these rocks all melted. And when that happened, the denser elements sank down through to the very core of the Earth, and the lighter elements floated at the top.
The huge gravitational pull dragged the heavy iron and nickel down to form the core and separated the rest of the planet into layers.
Okay, we're talking about the separation of the layers of the planet. And that process of separation is what we call differentiation. Okay, so that's your last vocab term for this video, and there's one other one that we'll add on to that in the next video. So the separation process, like I said, is defined as differentiation, and it's the separation of planetary material according to density. So the more dense objects are going towards the center, that's how we get an iron core, and then the lighter material, less dense material at the surface of the planets. So in terms of these definitions of this process, of course know your definitions, but also what's important is to know how do we get planetesimals by condensation and accretion. Once a planetesimal becomes a certain size, then we get protoplanets, and once become protoplanets, they become molten, and we get a differentiation process, and that's how we establish our different layers of our surfaces of our bodies. So we'll go watch the end of this section for the video.
What caused such a huge mass of rock and metal to heat up in the freezing depths of space puzzled geologists for many years.
We think it's from the incorporation of very hot radioactive elements. They're out there floating in space. As the Earth accretes, it includes some of this ferociously hot material. As it gets inside there, it begins to heat up the rocks around it. And if you build the Earth fast enough and you incorporate enough of this really hot radioactive elements, it'll be enough to melt the Earth from the inside out.
Only 30 million years after it began to form, Earth had become a giant round ball of boiling liquid rock and metal orbiting the sun.
Imagine a totally molten world. I mean, it had molten magma oceans, no dry land anywhere, no water, just flowing lava everywhere.
The temperature of the molten Earth was now a staggering 2,000 degrees. But at the edge of the planet, the vacuum of space is a constant minus 450 degrees, almost 2,500 degrees colder. The surface rock could not stay molten for long.
It's cooling from the outside in. So from the outside begins to crust over, and you get this little scab, like on a wound, of cooled rock, but still really hot, and then gradually begins to cool from the outside in.
Unstop right there. I'm about to pop a cap of fresh in that washer. With Unstoppables in...
Sorry about that. I didn't want you to have to watch the commercial.
In less than 1 million years, Earth's surface was covered in a thin crust. But volcanoes still spewed out lava and choking gases. Meteorites rained down in a constant bombardment. Earth had a long way to go before it could support continents, oceans, and life. Scientists investigating the earliest origins of the Earth have uncovered evidence from salt grains in space. They revealed that the Earth began to form when fragments of the solar dust clouds stuck together. The Earth's internal layers provide the clue that soon after it formed, the young planet completely melted. Scientists had worked out how the Earth first formed from a cloud of dust in space, but they were missing a vital piece of the puzzle. They still did not know the age of the Earth.
Okay. And of course, when we talk about the age, we've talked about some of those things in the previous lecture. So you're familiar with those things and how we've established the age of the Earth in terms of carbon dating of rocks and so forth. And of course, our solar nebula hypothesis. And so the Earth should be about the same age as the Sun. I will put the link to this video in the description so you can watch the rest of the video if you would like, but although it's not required. And so now you'll move on to the next video titled The Solar System Lecture Part 2.